going to establish how to find the Cartesian or scalar equation of the plane. So remember yesterday we worked on getting the vector and the parametric equations, but now we're going to be looking at the Cartesian, the standard form. Remember that standard form that we had when we were looking at this for lines? And so there was a standard form that was the same. So you could have different vector equations for the line, but you could only have one standard form, right? That's what the word standard means. Everybody will agree on that same one standard, all right? So you'll be able to find the Cartesian equation of a plane given different characteristics of the plane. All right, okay. Now, let me just start by reminding you about what we did yesterday. Yesterday we said that to write the equation of a plane, it would be in vector form, that is. It'll be x, y, z, which is equal to some point on the plane, which we'll call x0, y0, and z0, plus two direction vectors with two parameters. So two different parameters. The parameters could be the same, by the way, because that would just generate some different point, but we could have two different parameters. And we multiply those parameters by the direction vectors, and that will give us the points on a plane, right? The coordinates of a point on the plane. So this plane is a two-dimensional surface. So we would have understood that yesterday. It's a flat surface, and there are various points on that plane. So any vector that's perpendicular to it is called the normal. So if you just look at this diagram here, this flat surface represents the plane. And if I were to stick a line through that plane at right angles, so it's perpendicular to the plane, we call that the normal. We've used that term before, nothing new about it. But now we're going to use it to be able to generate a different kind of equation for the plane. Because we're going to say that this normal, which is going to denote by an n with a line over it, so it's a vector, right? If the m and the m2, so if we're talking about these two other vectors here are non-collinear, which we said was a condition of having to be able to have a plane. You can't have two direction vectors that are collinear. They would have to be non-collinear. So if these two direction vectors are non-collinear, so it means that you can't have them sort of lining up and moving in the same direction. They can't just take one and scale it and get the other one. They're non-collinear. Then if I were to take the cross product of that, that should give me this normal vector. We know that the cross product between two direction vectors gives us a vector which is mutually perpendicular to that vector, right? So that's what this normal vector is going to represent. And if we were to take that cross product and just, any value of k you want to use to scale it up, it doesn't matter. The fact is that it will be a vector which is at right angles to the existing vector. So let's make sure we're all clear on that. So what we're going to try to do is generalize now for any point that's on that plane, right? Using the information that we have here about the normal vector sticking up from the plane, right? At right angles to the plane. And that results from taking the cross product, as we said, of the two direction vectors. So hopefully we're all clear on that. So if we have a known point on the plane, so we'll call that, as I did up here, we call it x0, y0, and z0. Then we can find any other point on that plane in a generic way by taking the PO to P vector. What I mean by that is taking from that point, right, to just a generic X, Y, and Z, and then generate an equation from that. Hopefully that will make sense to you as we go through this. And it means that excuse me, that vector that we're generating that way is going to be at right angles to the normal vector. Because if you see any line that's along this plane here, so this vector here that's going from P to P1, P0 to P, right? Any line that I put along this vector, along this flat surface here, is going to be at right angles to the normal vector of the plane. So what that allows us to do is to say, okay, why don't we create a sort of a generic equation by taking the x, y, z, sort of the general point, x, y, z, and creating several vectors from that. And then if we multiply those two together, or dot those two together in a dot product, we should get equal to 0 because they should all be at right angles to the normal. Okay, so I know a lot of that might sound kind of far-fetched, but let's give you an example of what that means. So we're going to take this sort of general rule, which is take any vector that's sitting on the plane and multiplying it by that normal vector and setting that equal to 0. So here's what I mean by that on the next page. So here's a plane, excuse me, that has this equation, x, y, z equals, and they give it to you, right? Find the equation that results from what we just talked about, the specific point, the general point multiplied by the normal being equal to 0. Use the fact that any point on that plane must satisfy the equation, develop the Cartesian or scalar equation of the plane. First things first, we need the normal vector. So what I'm going to do is I'm going to go ahead and I want you to do this on your own, by the way. So don't depend on me. I'm going to go ahead and draw up my table. I know I use a table approach. Not everybody does. That's up to you. But I'm going to go ahead and figure out what the normal vector is to this plane. So these are two direction vectors at 2, -2, and 3, and -1, and 4, and -2. So those are my two direction vectors. And I'm going to go ahead now and see if I can find what my direction vector, sorry, my normal is for that vector. Okay, that's what I'm going to see if I can do. Right? And you can tell me whether you're getting the same answer that I'm getting. So I'm getting, so I'm putting my hand over the first column, that would be 4, and then -12, that should be -8. Is what I'm getting. You can tell me if I'm getting anything wrong here. Putting my hand over the middle, and I'm getting -4, and then -3. So that should be plus 3. So that should be -1. But I'm going to make that into +1, where we change the sign of the middle number. And then I'm going to put my hand over the last one, and that's going to be 8 -4, which is 6. Okay. You can confirm that for yourself. Make sure you're getting the same answer that I'm getting. Okay, if you're not, please let me know. But that's what I'm getting, -8, 1, and 6. You everybody's get the same answer. You should not be just watching me here, folks. You should be doing this for yourself. I've been making mistakes. I hope I don't make as much today, but that's what I'm getting. All right, don't forget to change the sign of the middle number. Okay, so -8, 1, and 6 represents that normal. So that's my normal. This is the normal vector. Right? So method 1 for getting this Cartesian equation, so there are two methods that I'm going to be going through. One is going to be a lot easier, but let's just simply go through this first method anyway. What we're saying is that if I take a generic point x, y, z, right, that would mean that I could multiply that generic x minus this point here, which is a point that we know is on the plane. So that's x -1, right? And that's going to be, and by the way, I shouldn't put the in the thing here. Let me just erase this. And why am I subtracting them? Let me just tell you why I'm subtracting. I'm trying to get a vector which represents a generic vector for the point and to some generic point that's sitting on the plane. Okay, so that's x -1. And then I'm going to say y +2, which means I'm taking the y value and I'm minusing -2, which is y +2. I'm going to multiply, and I'm going to put the third one, which would be z -5. Then I'm going to dot that with this normal vector that we just talked about and set that equal to 0, -8, 1, and 6. And set that equal to 0. What are we trying to do here again? Okay. What we're trying to do here, Ryan, I'll take your question in a minute. What we're trying to do here, Daria, is there a shortcut? There is. And I'm going to show you the shortcut later. I'm trying to justify why we're doing what we're doing. Let me take you back to the page that we had before. We're saying that if I created any vector on this plane, right, then going from any point that we know, so the point that we're using that known point right now, and creating a vector from that point to a generic XYZ point, just a generic XYZ point. Then if I multiply that by the normal, then because it's sitting on the plane, the dot product should be equal to 0. So what I'm saying here is I'm taking generic x and I'm minusing the x coordinate because I'm trying to get I'm trying to get a vector that runs from the tip to, it's in other words, this is just a vector that runs between these 2 points. That's really all we're doing, right? So this is my x component, which is the x minus the 1. This is my y component, the y minus 2, which is y plus 2. And this is my z component, which is z minus 5. So just think of that as being a vector that we're forming that sits on the plane. Okay. When I dot that with this normal, I'm supposed to get 0. So let's go. So I'm going to have minus 8 times the x minus 1 plus the 1 time, I don't really have to put 1 there, 1 times the y plus 2, and then plus 6 times the z minus 5, and that is equal to 0. Okay? And then all I need to do is just finish the math here. So that's minus 8x plus 8 plus y plus 2 plus 6z minus 30 equals 0. Then if I just sort of tidy this up, I'm going to get minus 8x plus y plus 6z. And let's see now. It looks like I'm going to end up with minus 20. 8 and 2, that's 10. Right, so minus 20 equals 0. So what we now have here is what we could call a standard form, except for one thing. We generally, and if you remember this from grade 9, when you're using standard form, you always like to have the x, and that's why it's standard. You sort of have some rules about what makes it standard. We're going to change that minus 8 into a plus 8x, which means we're multiplying everything through by minus 1. So 8x minus y minus 6z plus 20 equals 0. That represents your Cartesian equation. Surprisingly, remember when we're doing something like this for a Cartesian equation for a line, it was something that looked like this, but it was for a line. Now, when it looks like this, it's actually for a plane. So this is the Cartesian version of the vector equation of this plane. Okay, that's what this is. So that's method 1. It is no coincidence. It is no. Did we find a plane perpendicular to the plane above? Yeah, that's the normal. Remember, right? We took the cross product of the 2 direction vectors and got the normal vector. Do you remember that? We said the coefficients are just opposite to the normal. Well, they weren't the opposite at all. They were the actual numbers, because when we got it the first time, we had the minus 8. So yes, that's a good observation, Zia. We ended up with the minus 8, the positive 1, and the positive 6 initially. Minus 8, positive 1, positive 6. And then we had to figure out the c on the end afterwards. So you're absolutely right. We were the ones who multiplied it through by minus 1 to make it look like this. But yes, essentially, it really is the coefficients of these. The coefficients come from the normal. That's where the coefficients came from. So you're thinking, okay, there has to be an easier way to do this rather than going through all of that. And you're right. And this takes us back to how we got the Cartesian equation when we're doing this for a line in 2 space. So here comes method 2. You can almost figure this out for yourself. Using the coefficients of this normal, so the minus 8, the 1, and the 6, I'm going to say that I'm going to start off with minus 8x plus y plus 6z plus c, because I don't know what c is yet. Am I recording this? Yes, Ryan, I'm recording it. Plus c is equal to 0. Okay? And then, what do you think I'm going to do next? Once I've done that, I need to find the c now. Yes, Sia, go. Well, you need more than one position vector to find the normal. And that's why when you have a plane, you have 2 position vectors. Then you can multiply them and get what the normal is. You can't get the normal from one. Well, actually, you could get, not for a plane anyway, not for a plane. Plug in the x, y, and z. Thank you, Quinn. So remember now, x, y, and z is not these direction vectors. X, y, and z is the 1, minus 2, and the 5. That's what the the coordinates are for that point that's on the plane. And that's exactly what I'm going to put in. I'm going to go back up here. I'm going to find all these points, the 1, -2, and the 5. So -8 times the 1 plus, I forget what it was, sorry, plus the 2. Yeah, plus, no, -2. Plus -2 plus 6 times, I believe it was 5, plus C is equal to 0. Now, let me just go back up. Quinn is absolutely right about what he just said. Make sure I put the right numbers in. I'm not going to have a repeat performance from yesterday. 1, -2, and 5. 1, -2, and 5. Okay, perfect. So this is -8. This is -2. And this is plus 30. Plus C equals 0. These look a lot like what we had before anyway. So this is going to be 20 plus C equals 0. So C is equal to -20. So initially, we're going to have -8x plus y plus 6z minus 20 equals 0. And as we said before, really all we need to do now is just multiply everything through by -1. It's the same plane. It's the same plane. It's just being multiplied through by -1. So now it's going to become 8x minus y minus 6z plus 20 equals 0. Done. All right, same equation we had before, same equation now. So I'm not asking you to go through this process, folks. I'm not asking you to go through the method 1 process. No, I'm not saying that. Once we have figured out that these coefficients will come right from the normal, just go for it. I'm just trying to justify how it comes about, but you don't have to. I'm always saying look for the shortcuts, right? If you can see a pattern, math is about pattern recognition. I've said that a million times, well, not maybe a million times. I've said it a couple of times now. Then find that shortcut, which is consistently getting you to your destination, and use it. So there's your first answer. There's your standard Cartesian equation for the vector equation that started off looking like this. Is there another vector equation we could have put in? Absolutely. There are other vector equations. There's other points you could have found on the plane, right? And there are other vector, but doesn't matter what point you choose on the plane, right? If you had even different direction vectors, you would still end up with the same standard Cartesian equation. And that's the beauty of the standard Cartesian equation. All right. Okay, question. No, is there anything about question number 1 that we need to talk about before we go any further? Or is everybody clear on that? Okay, not having heard anything, I'm going to move on. The point, and they give you a point, is a point on the plane with a normal of this. Determine the Cartesian equation of the plane. Well, this is easy now. This is so easy at this point. If they give us the normal, and if they didn't give us the normal, we had to do some work to get the normal. They gave us a normal, right? So if we have the normal, we can go to town with this. We can say, okay, that means it's -x plus 2y plus 6z plus c equals 0. There's your starting point right there, right? Just use the components of the normal to start setting up your coefficients for the Cartesian equation. And as Quinn said a few minutes ago, we're just going to plug in the a value, which this is a point that's on the line. We need that to be able to create the equation. We're just going to go ahead and plug in that point into the x, the y, and the z. So it's -1 plus 2 times 2 plus 6 times 2 plus c equals 0. So this would be -1 plus 4 plus 12 minus 1. Don't start, Mr. Kamak, don't start. Plus 4 plus 12 plus c equals 0. So that means that c plus 15 is equal to 0. And therefore c is equal to -15. And our equation becomes what you expect. -x plus 2y plus 6z minus 15 equals 0. But standardized, it becomes +x minus 2y minus 6z plus 15. Just change the sign of everything. It's the same plane. What could be easier? So there's your answer. That took us, I don't know, 1 minute, maybe, minute and a half, perhaps, maybe a little bit longer. That's all. That's it. All right. So far so good, folks. Are we following along what we're doing? Sharujan, let me see what you think about that. Zia says yes. That's good. Sharujan says yes. Ryan, how about you? Did that all make sense? What we just did? Okay. All right, no problem. Quinn, that should be that should be the test. Yeah, right. We'll see what we put on the test. As I tell you, the question that we're gonna be doing, the last question today, is gonna be on the test. I'm telling you that right now, the 30. Yeah, right. Determining the Cartesian equation plane from three coplanar points. One of the ways you can define, of course, plane is by giving the points on the plane. So let's say that I gave you 3 points, and those are the 3 points. Homework question scares you? I don't know why it should scare anybody, right? We haven't even gotten to it yet, and you're talking about being scared. Anyway, so determine the Cartesian equation of the plane from three coplanar. Now, we did a question like this before we even got onto equations of planes. We asked you back when we were looking at combining 2 points and making them into a third point. We were saying that these points are coplanar, and we had to show that they were coplanar. Well, now we're going to come to the equation. Cross product, you say, Zia. Well, before we can do cross product, we have to go to what Quinn and Daria are saying and what Zia is saying, right? We have to find two direction vectors. So I see some suggestions here, A, B, and AC. Yeah, those would work just fine. And so let's go ahead and do that. So A, B, and AC. So A, B, doesn't have to be those two, by the way. You could find any other cross products you like, as long as they are tail to tail, right? As long as the two vectors are tail to tail. So we'll go with A, B, and AC. Yeah, those two vectors are in fact tail to tail. And let's see now, my AB vector should be, let's see if I can get this right now. That should be equal to 4, 0, minus 1. I'll double check that. So that's A to B. So that's 3 minus 1. 2 minus 2 is 0. 4 minus 5 minus 1. Okay. My AC vector should be minus 1, minus 5, and 1. I'll double check that. I'm taking C minus A, minus 2, minus 1. So that's plus 1. And that's minus 3 minus 2 is minus 5. And 6 minus 5 is 1. Okay. Hopefully everybody is fine with that. And yes, we now have to find, as Zia said rightly, the cross product between those. We need that normal vector now. So we're going to cross them. So let me set up my little table here. And of course, you should be doing the same thing and not depending on me, right? I mean, I'm not hoping to make the same kind of stupid errors I made yesterday. So 4, 0, minus 1, and minus 1, minus 5, and 1. Okay? So here comes my normal vector, right? When I cross these two vectors, I am getting, please check this for yourself. I'm not using the wheel today because I want to get through I want to make sure I get to that last question today, the one that's scaring some people. I'm not going to call any names, but yeah, some people who seem that they're a little bit apprehensive about it, but don't be, really, you don't need to be. Okay, so my cross product, let's see now, 4, take out that first one, so that's that's positive 5, sorry, minus 5. And my next one should be 3, but I'm changing the sign to minus 3. And my last number should be, let's see, put that there. That should be minus 20. Okay. Can you confirm that you're getting the same answer that I just got? Is everybody okay with that answer? Okay, Sharujan says, is it only Sharujan who thinks that answer is good? Okay, Baroka. Thank you, Lily. Thank you, Karis. Okay, thank you all very much. Okay, so we're ready to write our equation now because we're more than halfway there. We now have the normal vector. So all we need to do is take one of these points and plug that into the normal vector. Okay, let's get the normal vector starting off with minus 5x minus 3y minus 20z plus c equals 0. And for no particular reason, I'm going to use the 3, 2, 4. That's just the choice that I'm making. You don't have to, excuse me, you don't have to make the same choice. But again, you can try this for yourself. we should all still end up with the same answer. So I'm going to go to 3, 2, 4. So minus 5 times the 3, minus 3 times the 2, minus 20 times the 4, plus C equals 0. That's my choice. It doesn't matter which point you're absolutely right about that. All 3 points are on that plane. And because I'm doing this one, you can try another one and see what you get. Okay? So let me just make sure I didn't make any mistakes. I'm being so cautious today. So 3, 2, and 4, minus 5, minus 3, and minus 20. Okay, good. So I'm getting minus 15, minus 6, minus 80, plus C equals 0. Excuse me. So this looks like it is minus 101 plus C equals 0. All right. Again, check that for yourself. Okay. We don't want a repeat of yesterday. So therefore, that means that C is equal to 101. All right. And I'm going to go ahead now. Hopefully somebody's trying a different set of points, by the way, and see what you get with that. And if that is the case, and here's my equation, minus 5x minus 3y minus 20z plus 101 equals 0. But then I'm multiplying through now by the minus 1 to give us 5x plus 3y plus 20z minus 101 equals 0. Okay. All right. Did anybody try a different point to see what would happen? Or did everybody, I got positive 3 for the value of y before. Huh. Did I make a mistake already? I was hoping that I'd gotten much further than that. Yeah, I got the same value of C using point A. Same as B is what you're saying. Ashuruj, are you saying you got the same thing using point A? I got positive 5, 3 minus 20. Okay, but why is it minus 20 though? You got 5, No, you're supposed to be getting the same answer. All right, so I'm going to ask you to check it again. All right, remember that there are 3 points. Let's see which points you're using. You're using what, the minus 1, the 2, and the 5? Is that what you're using? Which points are we talking about here? I'm just curious. Using the points for C. So the minus 2, the minus 3, and the 6. All right. We can try this again later, but I really want to get through this. But I think you should get the same answer. You're supposed to get the same answer, by the way. You're supposed to get the same answer. Okay. All right. Let us move along to this one. Number 4. From the matrix. From the matrix. From the matrix. Oh. Are you using the minus 5, the minus 3, and the minus 20? Yeah. But yeah, and that sets up the coefficients though. Just so you know, you can't use that as a point. Just so you know, you need a point and you need to put in one of these points. Okay. Okay. All right. We can come back and look at it later on. Okay. But let's just see if we can power through the rest of the questions that are on here. All right. Reason with the parallel and perpendicular lines. Okay. So show that these planes, and they give you Cartesian versions of the plane, and they use the pi 1 and pi 2. We talked about this yesterday, that the pi is just one way that people refer to a plane, right? So the equation of a plane. So there are the Cartesian equations, pi 1 and pi 2, in standard form. And you want to show that these planes are perpendicular. Well, we don't have the direction vectors for these planes, but we know that they both have normals which would correspond to these coefficients. Well, if the planes themselves are perpendicular, then it means that their normals would also be perpendicular. So yes, Daria is right. Get their cross products and see what you get from the cross products. Because, again, let me say this again. If the planes both have normals, and the normals are, I'll show you what the normals are. The normals, and you should know this. The normals are 2, minus 3, and 1. Those are the normals. That's the normal for the first one. Normal for the second one is 4, minus 3, and minus 17. So these are not direction vectors, these are normals. Both normals come from the coefficients. But what I'm saying is that if the planes are perpendicular, then their normals will also be perpendicular. And that means that if we dot these, we're hoping that we should get 0. Okay? So let's go ahead and do that. Yes. And isn't it the dot product? Yeah, it's a dot product. Yeah, that's exactly what I'm about to do. Not the cross product, but the dot product. I just realized that Dara is saying cross is actually dot. Remember the dot product is the one that gives you 0 when they are perpendicular. So anyway, let's keep going here. So that's 4 times 2, which is 8, plus 9 minus 17. So 2 times 4 is 8. Minus 3 times minus 3 is plus 9. 1 times minus 17. And that's clearly equal to 0. Therefore, pi 1 and pi subscript 2 are perpendicular. Okay, I'll just shorten that. Okay. All right. So that was easy for us to do. There's nothing really particularly challenging about that one. Determine the angle. Okay, then. We can find angles between planes, right? We're given two planes, x minus y minus 2z plus 3 equals 0, and we're asked to find the angle between the two planes. What do you think? What do you think would allow us to find the angle between both of these two planes? Anybody? Anybody out there? All right. All I know right now is the equations of the planes, dot product. Well, the dot product is part of how we're going to find it. Yes, there's an equation. Position vectors? No, not so much position vectors. Dot product divided by the magnitude. There you go, Sharujan. Remember that we talked about a formula way back. And by the way, we're going to use the normals again. We're not using the actual planes. We're saying that if the planes have an angle between them, then their normals also have the similar angle between them. So again, we're using the angles of the normals to get the angle between the planes. So what are these two planes? These two planes are 1, minus 1, and minus 2. And if I have some time, I'll show you how we can establish this on GeoGebra. But I really want to get to that last question. We have to get to that last question. So I'm sort of making sure we have time for that by making everything else sort of stay there for now. But let's just keep going here. So that's a normal for this vector, 1, minus 1, and minus 2. And the other vector has a normal, which is 2, 1, and minus 1. 2, 1, and minus 1. Okay. Wouldn't the normal angle be supplementary? No. No, not at all. Because what we're saying, here's what we're saying, Zia. Consider that we have two planes right now, and both planes have an angle between them. So that's the first thing we're trying to find. That's what we're actually trying to find. Each of those planes has a normal associated with it. Okay, Zia? So what we're saying is that whatever angle they have between the two actual planes, their normals will also have the same angle between them. Okay? So we're going to use the formula that we learned a long time ago, like maybe 2 weeks ago. The cosine of the angle is equal to the dot product. So we'll call it, we'll take the two dot products. So it's the 1, minus 1, and minus 2 dotted with the 2, 1, minus 1 all over the magnitude of the two vectors. Folks, you got to remember this. So the 1, minus 1, and minus 2, and multiplied by the vector 2, 1, and minus 1. Okay. So the dot product in this case would be, what is this? 2 plus, sorry, let me just think now. Minus 1, okay, no, I'm saying that wrong. So it's 1 times 2 is 2, minus 1, okay, so that's minus 1. That's minus 1, and then plus 2. Okay, that's the dot product between them, which looks to me like that's going to be 3 on top. All right. With the no, okay. All right. And then the magnitude of the vector would be 4 plus 6 and 4, 5, 6 again. Well, it turns out if I take a square root times a square, and the cosine of theta is equal to that, by the way. If I take a square root times a square root, can we all agree that the result of that will be the number itself? Right? Good. And this works out to be a half, by the way. So if the cosine of theta is equal to a half, we've seen this before, then the theta is equal to 60 degrees. Thank you very much. So the angle between the two vectors is 60 degrees. The angle between their normals is also 60 degrees, just so that we're clear on that. All right, just want to make sure we're clear on that. Angle between the normals is also 60 degrees. Okay, have I got to the grand? Okay, so A and B of this question. Determine the Cartesian form of the plane whose equation in vector form is. You know what? I don't think we really need to do part A of the question. Not that I want to dismiss it. I'm just so eager to get to part B. Sorry, folks. You all know that if I have it in vector form, I'd have to find the cross product of these two and then put that point in, right? Folks, can I confidently say that part one is too easy and I'm insulting you by even bringing it up? Thank you. I appreciate that. And I apologize for insulting you that way. Let's get to the real sort of more interesting question. And this is your homework now. This is the one that's on the homework. So focus in, and I'm going to show you how we're going to do this using the GeoGebra. We should have time, but about half an hour left. Determine the vector and parametric equations of the plane with a Cartesian equation of this. So we're trying to go backwards now. We're trying to come up with a vector. And it's not, when it says the vector and parametric equations, I wouldn't say that there's the vector. There is more than one vector equation. And there's more than one parametric equation that we can come up with. We're going to come up with one. So here's our problem, right? We don't have any vector. I mean, we knew how to take a vector equation. So this one we can do, right? We can come up with some Cartesian equation for that. But what happens when you start off with the Cartesian equation? Does anybody have any ideas that we can sort of, we know the normal is that, yeah, that's true. That is a normal. That's true. Absolutely, that's the normal. But how does that help us to come up with the vector and the parametric equations? That's a good start though, Daria. But where do we jump off from there? Where do we go from there? Right? That's the thing we need to kind of try to figure out now. Can we do something with the cross product then? Well, what we're going to cross it with though, because that norm is a result of the cross product. So it's kind of trying to work backwards. But we don't have the two pre-existing vectors for us to work with. You see the kind of dilemma that we're in here? Right? That's kind of a problem, isn't it? Right? How do we go backwards now from the Cartesian and create vector equations that have, can we do something? Okay, does anybody have any ideas? I see what Daria is saying. I see that, right? But what do you think? Is there any other ideas that you think? We know the normal, yeah, that's true. 1 minus 2 and 5. How about if we had some points on the plane? Would that help us? Because look, let me take you back a bit here. We were given 3 points here, remember? And with those 3 points, we were able to create a vector, well, a Cartesian equation in this case. But we've used 3 points before and come up with vector equations. Omit vectors from the intercepts. Okay, that's certainly one way to do it. But I'm going to show you where intercepts is 1, but that might be a little tricky because some of these intercepts might not even be integers. They may be very difficult numbers to work with. So let's see if we can come up with 3 points on the plane. So watch carefully now. So I'm thinking, okay, here are the 3 parts of the Cartesian equation. What about if I were to stick a 0 in there for y and for z, right? What would that, and that's what kind of Dara is talking about, finding out those intercepts, right? Could we find the x-intercept that way? Of course we could. Because if we were to take 0 and put 0 in for the x, then I'd have, not for the x, sorry, for the y and for the z, I'd end up with x minus basically 0 plus 0 minus 6 equals 0, right? So that would mean that if my two y and z coordinates were 0, then my x coordinate, and that of course means that x is equal to 6, by the way, then that would mean that one point on the line, we'll call this point A, would be 6, 0, 0. Can we first of all agree on that? Does that make sense? Perfect. So one point on this plane is 6, 0, 0. Now let's find some more. What about if I kept my, let me do the easier one first. What about if I put 0 in for my x and 0 in for my z? What if I did that? Then what I'd end up with is, right, just think about that for a second. Now there's no x there and there's no z there. I'd end up with minus 2y minus 6 equals 0. That's what's left, okay? X is gone, z is gone, right? So I have minus 2y minus 6 equals 0. So that means that minus 2y is equal to 6. And therefore, y is equal to minus 3. So what we're saying is that this second point, this b, whatever letter you want to put on it, right, is when I have a 0 for my x and a 0 for my z, my y value is minus 3. Okay? So far, so good. Are we good so far? The last one is the trickiest one, right? And we're going to still come up with a point for that. So what if, so I made zeros out of the y and the z, and I got an x value, and I call that one 600. I made the y value, I made the x value and the z value 0, and I was able to come up with a y. This is really the y-intercept, by the way. But now I need to work on maybe putting these two as 0, and let's see what happens with that. So now I'm going to end up with 0 there and 0. I'm going to have 5z minus 6 equals 0. And I honestly do not want to make this into some fraction. Put your hand up if you want to deal with the fractions. Put your hand up right now and say, yes, Mr. Come give me the fractions. I'm good to go. I don't have a problem with fractions. Anybody? Anybody? Nobody. Come on. You don't want to have fractions. Is there perhaps an x value I could put in so that if I were to put this in here, then I would in fact end up with a 0? Is there any value of x? So 5z, so we have minus 6. Can I stick some value in here so that when I try to divide by 5, here's the thing. If I try to divide by 5, then I would end up with a nice whole number. Is there a value of x that could make that happen? Can you think of a value of x that would, I see what Dario is saying, but can you think of a value of x that if I were to put that there, then that would make this equal to 0? Give me a value of x that would work for that. Anybody? So 5z minus 6, but that's what's here. That's this part here, 5z minus 6. But I don't want to make the x 0 anymore. I want to make minus 4. There you go. Let's try that. So if I did that, then I'd have this. 5z minus 10 equals 0. So therefore 5z is equal to 10, and therefore z equals 2. So here's what my next point is then, my C point. I have an x value of minus 4. I have a y value of 0, and I have a z value of 2. Okay? Is everybody? No, if I put 6 there, let's see if 6 would have worked. So if I put 6 there, I'd have minus 6. Oh, I see what you're saying. Putting in 6 there would have worked because then it would have been 0 as well. Yeah, you're right about that. That would have worked as well. Okay? So you can put in any value that's going to give you a nice, neat whole number. I personally wouldn't want to have to deal with any fractions. Okay? So put in any value, but you just have to remember what value put in, because now I'm not saying there's 2 the other points we had 0 and 0 here for the b, but now I need a minus 4 for the x. I'm still putting the 0 in for the y, and it worked out to be 2 for the z. Now, what I'm about to do now is take you over to GeoGebra. We're at 2:19, about 20 minutes left. I'm going to take you over to GeoGebra now. I'm going to stop sharing this, and I'm going to show you. I'm going to first of all put in the equation. If you put 6 in, you have 2.600. Yeah, yes, you would. That's fine, Shirujan. We have 600 already, remember? So we have 600, that was our point A. And yes, Ryan, go ahead. Yeah, yeah. I'm going to show you fractions. Why do you want to go with fractions? Why does that? Why do you want to do that? All right, let's try to get over it. Let's try not to do that. I mean, I can show you to put a fraction in, but let's try not to do that. I'm going to stop sharing this. Oh, if I stop sharing this though, I'm going to have to. All right, I'm going to stop sharing this, and then I'm going to pull up GeoGebra, and I'll start recording that as well. All right, because I need you to be able to put that together with what we're doing now. So I'm going to stop sharing this. Hopefully, everybody's written this all down. So we have 3 points so far: 600, 0 minus 30, and minus 402. Now the truth is that you can create your well, let's just do it right now. Let's write our equation right now, our vector equation. Right now we know that we have 3 points, right? We need to get some direction vectors. Let's take our AB vector. Let me just finish this up first. And our AC vector. Right, we'll do that. AB vector and our AC vector. We'll write our equation and then we'll go into GeoGebra and finish up. Okay, so my AB vector, excuse me, right? My AB vector would be equal to, let's just make sure I get this right now, AB, so that's B minus A, so that would be minus 6, and that would be minus 3 and 0. That's my AB, so that's B minus A, minus 6, that's minus 3, okay. And then my AC vector, so that would be minus 4, minus 6 is minus 10, and 0 minus still 0, and 2. Okay, so hopefully everybody's following along with what we're doing here. Are you sharing? No, I'm not sharing GeoGebra yet. I just want to finish up writing the equation first, and we'll go up to GeoGebra afterwards. Okay, so those are my AB and my AC vector. I'm ready to write my equation now, my vector equation. So I'll call it pi is equal to, I'll take any point. We have 3 points. We'll take the 6 zeros. I don't really care which one. 6, 0, 0 plus m times one direction vector minus 6, minus 3, and 0 plus t times minus 10, 0, and 2. Okay, so now I've been able to put together a vector equation based on the original Cartesian equation. Is it the only one? Of course not. For one thing, I could have chosen different vectors for my direction vector. I could have done BC and BA, right? I could have chosen a different point, right? It still leads me back to the same place. Now, let me stop sharing this. I'm going to stop my recording so that I can start recording my GeoGebra page. So folks, please put down, make notes of everything that we've done so far. It will be in the video, but it's good if you have your own notes, okay? So please make sure you have your own. I'm going to stop sharing this now. Let me just say that again. So stop sharing that, which means, okay, so you can see that I'm recording this particular screen now. So I'm going to go to the 3D again. And then I'm going to see if I can put all the stuff in that we started off with before, which is the first thing was the what you call it again now, the Cartesian equation. Let me scroll up and see if I can find that Cartesian equation again. So it's x minus 2y. So x minus 2y, see if I can get it right this time, plus 5z, and minus 6 equals 0. Minus 6 equals 0. Okay, so there's my plane. Oh, hold on. Sorry, I just realized that you weren't seeing that. I'm sorry, folks. Sorry. Now you can see it. Okay. So there's my plane, first of all. And now I'm going to put in the points that I said were on the plane, if you remember. Open a bracket, by the way, when you're doing that. 6, 0, 0. It will label the plane, the point for you. So that's your first point. And then our second point was, let me just scroll up again, see if I can get that from you. 0 minus 3, 0. So 0 minus 3 and 0. I'm just doing this again so that it will be in the recording. Then my C point was minus 402. Minus 4, comma 0, comma 2. Okay, and we showed that all of these points were sitting on the plane, right? They're all on the plane, sitting right there on the surface of the plane. Hopefully that's obvious. And then we said we needed some vectors. So we need the AC and the AB vector. And you can easily ask GeoGebra to give you those vectors. So vector, and it says start point, end point. So my start point is A, and my end point is B. So it tells you what the components of that are. I can do the same thing for my other vector. I'm just repeating this so that everybody, it'll be on the recording. And I'm voting for the AC vector now. So I'm going to start by typing vector again. It's going to ask me, not this one, get rid of this actually. Delete. Let's try that again. So vector, start point, end point. So I need my AC this time. A and C gives me what the vector is. So my next step now is to combine them into, so we see the vectors, by the way, are sitting on the plane, right? Clearly sitting on the plane. And my next thing is to write a vector equation, or a plane equation. I start by typing PLAN. So it's going to ask point, vector, vector. So my point was, I'll use the A, that's what we used the last time. And my vector is a U and the V vector. U and V vector, right? And what you notice is that I get a new equation, a new plane, which you can't distinguish from the other one because they're sitting in the same place. Okay, so let me show you how to share it one more time, right? So I'm going to come over here in the corner, click on that little, not so much a waffle, those 3 lines there, go down to share, not save, but share. Give it a name, give it your name, MC, press the save button. And in a little while, it will come up and give you the option to copy that link. And that's all I need from you. So when you go to your homework, you just paste that little link in the box. When I click on that link, it will take me to the GeoGebra page and I will see all I need to see. All right? Can you please paste the link here? Okay, no problem at all.